I have now recording.
Okay. Welcome to lecture number 5. Sorry about the delay. We were allocated with a room KE1091, which happens to be a lab space, and it was already occupied. So, okay, next week we'll that will change for sure. Okay, so we're 15 minutes late, so probably we will stay 15 minutes longer, if that's okay with you. Alrighty. So, just a reminder about the schedule. We are now in week 3. This week we have 2 lectures. I will cover the slides at 3 and hopefully start with slides at 4 tomorrow, downlink. And then I aim to complete most of the downlink multi-user MIMO capacity discussed on slides at 4 during next week. And then there will be a second exercise given next week's Thursday. So we will post the exercise hopefully tomorrow. So on Thursday you can give some hints in the exercises. And the first midterm exam is in 2 weeks, right? Tuesday. Mine. Okay. All right. Let's get started with the topic. So last time we were discussing about the multi-user diversity. And so that the multi-user diversity actually starts to diminish quickly when we increase the number of antennas. So we notice that if the number of antennas becomes very large, the distribution of the norm of the channel becomes really peaky and concentrated around 1, right? Normalized norm of the channel. So when the NR goes to infinity, the normalized norm goes to 1, right? So so basically, in other words, when we have a large number of antennas and IID fading, it's not very practical, we don't get any selection gain, right? Because all the users have at the output of the match filter, there's no fading, it's deterministic. The channel becomes like this. So in the but for the single antenna case, we had this strategy where we choose the best user at given time instance, right? And we plug in this to the ergodic capacity formula. Voltage 1 plus XR, and then this let's say HK star with that star strategy. And then we can apply the density inequality or a concave function. So this is upper bounded by, so we can take the expression in this side. Right, that's the inequality. So we get log 1 plus HNR expectation of this HK star squared. And you might recall from the the wireless communication tool, that this expectation, when the number of users k goes large, you can approximate this with log e of k. Right. So this becomes also determined. Then we have log, and then assuming that this becomes large, we can just remove this 1 plus. So we have the capacity is approximately capacity with this 3D some rate optimal 3D user selection becomes double log 2 log e k, right? And that you can see actually on the shape. This is the signal number of users given SNR. Some capacity grows double logarithmically with respect to k. So double logarithmic is, of course, it saturates very fast, right? So when you go to 100 antennas, you will have just a double log increase in the rate, right? So very little gain. Most of the gain you can actually from going from 1 in 4 years. This was the Finland application. Now in this particular case, we have 5 antennas. You still get some multi-user diversity gain, selection gain, right? But this is actually so AWG and capacity is 1. So the relative gain from choosing the best user at the output of the match filter gives you much smaller relative gain with multiple antennas than with single. Here you can see that you get with 30 users, say 20 users, you get about 2-fold capacity gain with respect to AWG channel capacity, single user AWG capacity. But here, it's high antennas, you just get the fraction. You get 30%, right? And obviously, when the number, so this one here is the beamforming gain, right? When the number of antennas increases, obviously the capacity increases as well because you get beamforming gain, right? But the relative gain from choosing the best out of k users decreases. It goes to 0 asymptotically. Then R goes to infinity.
It seems that the sound quality is not good. It is maybe due to the internet.
Internet is not.
Internet is not good here. Internet is unstable.
We have one cable. Can we can direct?
Are you using
I'm using Wi-Fi.
an old?
Yes, yes.
Can you use your
Oh,
phone? Sorry about that. How is the quality here? Okay. Okay, let's take a little break to change that.
Okay, I change it to my phone.
Okay.
Should be okay now.
How bad was the quality? Can someone comment from the Zoom session?
Is the voice quality good? Okay now? Okay now?
Now it's better. No,
Anyway, the quality is good now.
Yeah,
they are not telling me.
I'm not
Okay.
telling anything, but the internet should be fine now.
Okay, oh, that's the most important. Okay, let's move on. So that was the single user selection policy, but okay. What if we have multiple antennas and we have, let's say, a scenario where K is larger than NR. Right? So obviously the capacity optimal solution, we know, just allow every user to transmit and apply MSSC receiver. But if we now want to do something simpler, we discussed about this grouping policy, right? That choose at most NR, like a subset of NR users from K users, right? So we could choose, like for example, user 1 and 2, users 3 and 4, or any combination, or any time use. Like round robin would be just going through all the combinations. Or whatever, you can apply whatever scheduling policy on top of that to provide some fairness. So obviously here it's like this is strictly suboptimal policy, choosing one user at a time, because we are not using degrees of freedom. Here we will be using all the degrees of freedom. Right? We are choosing always as many users as we have degrees of freedom. Degrees of freedom in this case is always by the minimum of NR and K, right? K is larger than NR, so if you think about, let's say simple projection to this standards projected to a 2D, let's say you have a user 1 here, this H1, then we have H2, we have H3, and H4. How would you group the users in this particular case? Any idea?
One on H3 and then H2 and H4.
Yes.
So they're all
We are nearly orthogonal, right? So obviously, if we choose user 1 and user 3, you can see that almost the match filter projecting one user to other users' null space does not reduce the gain, right? Because they are already almost orthogonal, right? On the other hand, scheduling user 1 and user 2 is not that good strategy because they are more dependent, linearly dependent, right? If you have, for example, another user, let's say user 5, which is almost wholly now with user 1, this would be the worst possible pairing, right? Because after projecting the user 1 to the null space of user 5 and other way around, let's say here's the null space of user 1, projecting user 5 to null space. The gain would be very small, right? And vice versa. So in this case, good strategy for grouping would be H1, user 1 and user 3 and user 2 and user 4, and perform TDMA or FDMA. Which domain these channels are. Okay. And in general, good really strategy how to use it, how to choose users. If you have K users, you can start from any user, but if you want to, for example, maximize the sum rate, you want to choose NR users out of K. What would be the best NR users out of K? So pretty strategy. You just pick the first user to be argmax K HK. is the strongest user, right? The user with the largest norm. Okay, that's the first user to be picked. And then you project all the users. Project all the other users, remaining users. Let's call this set of selected users to be. So after this first step, user 1 goes to set of selected users. Let's say K. Right? This is a set, and it includes just one user at this point. Okay. Now you can project all the remaining users. Okay, sorry, not the one. Let's say K star. K star index could be user 4, user 3, whatsoever. That's the index of the user that has the highest norm. So this goes to this set K. Okay, and now you go through all users I that do not belong to this already selected set of users K, right? If you have 5 users, you go through 1, 2, 4, 5. It's 3 users. 3 was already selected, right? And then project every user. There are 2 ways. Basically, you can compute the projection vector, or you just we remember from wireless communication 2 that the projection vector, the null space of all users that belong to that already selected set of users is I minus H revision H bar. Here we have the HI. And now this H includes all the users, the user vectors that are already selected. Right? H. It gets a bit complicated now. The first user in K to the last user cardinality that K, right? So obviously in the first step, this includes only user 3 that we already selected. It's a vector, right? So this could be simply H3 in the first case, the rank 1 matrix. Okay. So this would be actually projection of this would be the projection operator. The projecting every user I to the null space of already selected users. So the one that maximizes this projection is selected, right? This means that it's the most orthogonal, but it's not only the most orthogonal, but it has the highest projection, highest gain after projection. So it includes also the norm of the chunk, not only the angle or the orthogonality, right? You can have an orthogonal vector, but very small gain, right? So this takes both aspects into account at the same time. For example, if you have a space, this would be the space H bar, and now we want to find. Imagine we have a different standards here, and we want to choose out of these remaining users the one that maximizes this projection, right? When we project all of these vectors to the null space, right, which is orthogonal to the already selected set of future channels, we can have, for example, a user with very large channel gain, but not as orthogonal as another user, right? But with smaller gain, we might still want to choose this user because the gain of the projection would be still the largest, right? This could be actually good homework.
But
To
that
see
user
what's the benefit, how this works, and how much you gain from this selection.
but
Write it
that
down.
user could be already selected in the first place, right?
What's that?
That user could be already
That's a good
selected
point,
in the
yes.
first place.
Of course, if that was, I mean, if the first user was this guy, right?
Basically, you're not doing the normalization here for the HI.
What's that?
We are not doing the normalization for the HI.
You can also do the selection by you just choose the, that is just the scalar. It's like the SNR of the projection. Okay, we might give some more details for the homework if we come up with homework related to this user selection. Okay, so this would be 3D selection of NR users out of K users. Right. So if you plot how the capacity would, this would be the K, and then of course the capacity would increase like that. That would be the optimum capacity with MMS6. Then the linear strategy would be also with 3D selection. It would also increase. There would be a gap, but the gap would diminish when the number of users becomes larger. Right. All right. Any questions at this point? More or less understandable. We might come back to this scheduling and beamforming when we discuss about linear beamforming in slideshow 5. Okay, let's move on to one step ahead. Now we cover the multi-user minor modeling with single antenna transmitters. Simple extension now have multi-antenna transmitters, multi-user MIMO. So, received signal now consists of transmitted signal vectors, xk. So we have now two users here. In this particular example, we have x1, x1. So now matrix and vectors plus h2, x2 plus n. Right. So the x vector basically is one from here, and then x1, 2 from here, x2, 1, x2, 2. And the x vector is simply stacking xk, xk1, xk2. In this particular case, we have two transmitters. And the channel matrix in this particular case will be 2 by 2. Two transmitters, or 2 by or nt, sorry, nr by nt in general. matrix NR NT. Okay. But otherwise, it's the power constraint now here, we have a some power constraint per user, right? So this is basically taking the covariance matrix, trace of xk permission, which is the same as trace of kx k covariance matrix of user k. So the transmitted power, which is basically trace of the k transmit covariance matrix, is upper bounded by user specific power constraint. Okay, what about capacity region? Again, simple extension from the signal antenna case. Again, this is a two-user example, right? So we have these two users. So we have three constraints for a given transmit strategy. Let's start with an assumption that transmit strategy, the transmit covariance matrices are fixed. Okay. One possible strategy, if you don't know the channel, what would be the transmit strategy? What would be the transmit covariance matrix if there's no CSI there? Transmit. What would be KX1? Diagonal matrix, yes. And what other terms in the diagonal? T over NT, right? So dividing the power equally between transmit antennas. K over NT. Right. This would be the transmit covariance matrix. If you don't have CSI, you cannot do anything, right? That's simply transmit a single stream per antenna. Or well, you can choose for a subset of antennas if you like, but in general, it doesn't help much. Okay, so let's assume that the transmit strategy is fixed. Now we can we have a rate region. It's a pentagon. We have three constraints. What are these three constraints? Well, okay, they are. But we can start. We can take one step back and start from the visual information, right? So the rate of user 1 is upper bounded the case when the user 2 does not exist, right? It has been removed. In this case, y x1 x1 plus h2 x2 plus n. Okay. The best case from user 1 perspective is when this user is not there. Right? The single user. Right? This would be visual information between x1 and y given x2, right? x2 is removed. Y given x2, no uncertainty from x2 less than y. So you can write this as h y given x2 minus h y given x1 x2. If you don't remember these rules, you can always go to the Venn diagram. Always. Y, x1, x2. Now we are interested in this area here, right? Mutual information between y given x2, right? It's this area, and x1, this area that we are interested in.
But in general, x1 and x2 should be independent, right? Should they have some mutual information?
Yes, of course, x1 and x2 are, well, they are not fully independent because how you generate x1 depends on x2 optimally.
Is it
right?
downlink or uplink?
What's that?
It's uplink, right? In uplink, they should be independent, right?
No, well, if you think about the covariance matrix, how you design covariance matrix, user one,
They made
covariance matrix, they depend
on
each other, right?
Yeah.
If you want to favor user one, you have to, assume that user two is not there, right? So you have to take, when you design x1, you have to take into account x2 and vice versa. But it's just a general way to depict it. Okay, so you can compute mutual information. For example, differential entropy Hy given x2 minus differential entropy of Hy given x1 and x2. This would be this area, right? So this area minus this area gives you the intercept, right? And it's right here. Okay. And this is obviously, when you plug that in, you have log that by E. Covariance of Y given x2 is just the covariance of 1 and noise. So we have H1, 3x1, H1, I minus the log of noise. Which is similarly for user 2, user information between x2, y given x1, let's change the indices, and user information between the joint distribution x1, x2, and y, right? Which is h of y minus what? We're interested now this area. Differential entropy of y minus differential entropy of what?
Y given x1, x2.
Y given x1, x2. Which is when you plug in, gives you this one, right? All right, so this is the, so now this is for given, for any transit covariance matrix. So you can see that the shape of the pentagon, we will see that in the following slides, depends on the actual kx, right? So the rate region, again, is a union of all these pentagons. You have a pentagon for this pair of transit covariance matrices. But you have a different pentagon for a different pair of transit covariance matrices. So to come up with the rate region, then you have to take a union of all these feasible pentagons. The feasibility means that for any realization of kx, the power constraint has to hold, and the powers have to be positive. This kx has to be positive semi-definite. What is positive semi-definite? So you can have you can write it like this, that for any this product, this is a vector, it's just a random vector, z. So this product, z permission times kx times z is positive for any non-zero vector, right? For all that non-zero vectors. Another way is that if you take the eigenvalue decomposition, kx, you can take eigenvalue decomposition, let's say q lambda q permission. So this implies is that all the eigenvalues have to be non-negative, positive, larger than equal to 0. That's the positive semi-definite. And this is useful when we pose this problem as convex and write them as semi-definite problems. By the way, if you now similarly, now we have this two-user case, but you can actually H1, H2. You can write this system model equivalently as H bar, X bar noise, where H bar is simply stacked. It's a matrix where you stack all the users with the matrix, right? And then X similarly stacked. It's equivalent point-to-point MIMO. Now, unlike a point-to-point MIMO where you have a single power constraint, now you have like power constraint specific part of the matrix. So it means that the kx bar has to be block diagonal. The zeros here means that there's no cooperation between transmit groups of transmit contacts, right? If we have plug them together, connect them by a wire, then you can consider this as a single transmitter with k times mt on that, right? And then you can have full transmit coherence and full cooperation over antennas, right? This is the connection to a single point-to-point wire. Okay, let's take a 5-minute break and continue with more details. So, are you?
Yes.
Okay, there was a question how to set the power. So the power, see, the definition is general, so you can take this as the received power. So it includes the actual transmit power in dBm, watts, whatsoever, used as the transmitter, and then the path gain, right, for path loss. So it's just a P, assuming that the channel is normalized. So this P is the received power. Right. And you can run it also. You can include the path loss in the channel itself, and then use the actual power and then the actual noise, thermal noise level, everything holds. It's all relative. The SNI is the same. Make sense? Okay, transmit this architecture. Now, just like in the point-to-point MIMO, we can split the transmission to a pre-coder matrix. Then we have these individual streams. So this pre-coder now, the dimension of the pre-coder is NT times NK. NK is now the number of streams that we transmit per user. Number of streams is upper bounded by the different thickness data of individual channel matrix, right? In of NTK and NR. But it can be less, especially in the lowest NR. Doesn't make sense to transmit more than one stream. Focusing all power on stream per user. But unlike in doubling cases, as we will discuss later, the number of streams per user, because of individual power constraint for the fixed channel realization, for one channel realization, if you do the optimization for one channel realization, you will always have at least one stream per user. Right? In rounding, with some power constraint, you have the full classification. Allocate the power across users. If you have individual power constraints, always allocate one user. Of course, if you have an average power constraint over time, then there might be time instances. When you do the optimization over space and time, then there might be time instances that some users they don't transmit at all. Right? But for a given channel realization, if you optimize the transmit covariance matrices for given channel realization, then you always allocate at least one user in the capacity optimal scenario. Of course, if you are scheduling the linear strategy, then you use DNA to serve subsets of users if K is larger than N. All right. So here is that kind of recording matrix or rotates. Well, we can call it recording matrix or beamforming matrix. All terms are used. In the single user case, you know that if we have the full CSI, the single user case, you simply take an SVD, SVD of the channel matrix H, and the transmit covariance matrix would be simply the permission. B is the right singular vector. Key is to be the auto-filling power allocation. You can do this also for a multi-user case. You can optimize them individually, right? But it's suboptimal. Right? It's really suboptimal. You will see this. This could be actually one special case. So for both users, you can do SVD and then construct KX. Assuming there's the other user is not there, right? You can still use that KX for both users, but it's suboptimal from summary perspective. So in general, this KX should be jointly designed. There are, of course, instances when, and we will discuss that, where one user covariance matrix can be designed assuming that there's no interference from the other user. But then this transmit covariance sets an absolute preference to that given user. We will discuss that a bit more in detail later. Okay, receiver structure. Again, extension of the single antenna case. Now we have multiple streams per user. So first, the network decides the decoding order, right? The decoding order determines the rate per user, but it also determines the rate per stream. Now, if we have stream-specific processing, we have to also when we assign the rates per stream, we have to also assume a certain decoding order, like stream-specific decoding order. Right? So now we have decided that okay, user 1 is decoding first. Right? That's lower priority, it's decoding first. User 2 is then decoding second without any interference. And then we choose one stream. From the user sum rate perspective, it doesn't really matter which stream we choose. Stream specific rate changes, but the sum rate does not change. Sum rate is the same for both orders. For stream 2 first or stream 1 first. Okay, so we assume that stream 1 of user 1 is decoding first. So we have to compute an MMSC receiver. How would be the MMSC receiver for this case? So we have this model here. Y equals x1 plus h2 plus 1. So we can further split user 1 to two streams. We can first define x1 to be the u1, p1, d1. d1 is now the normalized data vector that we transfer. This is the power allocation matrix, and this is the normalized decoding matrix. Okay, just like here. Now we also include the power. So here, x11 has power p11, and x12 has power p12. So now we take the power apart and get normalized symbols v. So v1, the vik, and expectation of v1k is 1. The normalized data symbol. The key thing with this normalizing this data is that when you take an expectation, it vanishes because it's 1. Right? All right. And similarly, x2 is u2, p2, square root. All right. So now we can split. We are interested in stream 1 of user 1. So we can split the transmission or the system model to stream specific. So we have H1, we have U. Okay, let's assume that we have two streams, U1, U11, U12. Right? So this is a matrix that contains two decoding vectors for user 1. So we have H1, U1, square root, U11, sorry, P11, D11, plus the other stream of user 1, which would be seen as interference, H1, U12, P12 square root, P12, and then user 2. Okay, we can start it in the matrix form. H2, square root. Of course, we can split this one into separate streams, but it's the same as writing it in the matrix. Okay, so now we are interested in detecting D11, right? So we would like to detect an estimate D11 out of Y, right? We need to find the optimum beamformer, receive beamformer for this stream 11, right? So we have to find a beamformer W11, which helps us to extract D11 out of Y, right? So if you think, we have seen that MMSC previously, the MMSC receiver, it's also the information lossless, so we can assume MMSC SIG structure, just like here, and use MMSC receiver optimized for stream 1 of user 1, assuming all these other streams as interference. So what would be the MMSC receiver? Can someone tell? What should go inside the inverse? General Y of Y, right? We have seen that. So everything should go inside, right? So we have H1, U1, E1, U1, H1 plus H2, U2, E2, U2, H2. So this is the same as KX1, and it is KX2 plus M0I. What about the match filter from? It's now optimized to stream 1 of user 1. What should be here? Anyone? H1. U11 square root. Right. So this would be the MMSC. It's the true MMSC, right? Of course, from the SINR perspective, we have the other version where we exclude the own term. From the SINR perspective, it's the same. Right. You have seen that from the first homework. So everything extends. It's not just a extension of the single point-to-point case, single antenna transmitter case. Let's go to the stream domain, and you can come up with the MMSC receiver express. Okay. All right. Now you have decoded stream 11. Okay. You can subtract. Now you can reconstruct. Okay. This is of course capacity optimal strategy. So you have to basically reconstruct D11 for. You have to collect all these samples for capital N transmit intervals, right? So that you can then, after decoding, come up with the actual data symbols. And then you can reconstruct all these. I'm ignoring here the time index n. So for each time index n, you can reconstruct these terms, right? And you can subtract. And then you have equivalent receipt signal model without the first string. Okay. Then you move to the second string. What would be the MMSC receiver for the second string? How would it be different from here? Just remove this and then change the index here, right? Otherwise the same. Okay. And then you get an estimate of P12. Subtract both terms, both streams of user 1, and then move on to user 2. Okay. Receiver stream 1, user 2, and streaming interference from stream 2 of user 2. Okay. And finally, and you can then remove also that component from the receive signal. And finally, we are subtracting all the interference from that last stream to be decoded, and the MMSC receiver actually becomes the same as the match filter because there's no interference there. Okay. So this is the reception strategy. Okay, we discussed that if the transmit covariance matrix still a pentagon, right? We have to compute this rate, 3 rate constraints for fixed transmit covariance, fixed pair of transmit covariance matrices. So this is a pair of transmit covariance matrices, 1 and 2. So we have 3 constraints. We have the single user bound for user 2. Okay, let's start from single user bound for user 1. So the rate of user 1 is upper bounded by this locked form. So all the rate points smaller or equal to value are feasible, right? If you go beyond infeasible, there's outage. Or you cannot be decoded with 0 level. Similarly, other rate constraints, 2 user 2 rate, single user rate is upper bounded by this quantity here. All the points below are feasible by user 2. But then we have the third constraint, which is the sum rate constraint. It's this line here. The sum rate R1 plus R2, principle any combination of R1 and R2 given this quantity, right? So basically, it defines another line, right? So R1 has, in principle, this constraint you could have a R1 plus R2 point over here, right? This would be the maximum R1 plus R2 from R1 perspective, but this would be infeasible because R1 is bounded by this one. So now we have this intersection of 3 constraints, which gives that pendulum. Okay. So we have one decoding order, we have 2 decoding orders. Okay. So what would be the rate of user 1 if user 1 is decoded first? How would you compute rate of user 1 if it's decoded first? How would you start computing? We are interested in this area. Initial information of what? At the Venn diagram. Well, here it is. X1 and Y, right? We haven't removed X2. It's not given X2 because X2 is still there, right? And how do we write this in terms of differential entropy? H of Y minus H of Y given H1. Okay, then it's just plug and play. We always know that for a vector, the difference of entropy depends on the covariance of that vector, right? So we have log that i.e. covariance of y, which is all those terms there. We have h1, kx1, h1 remission plus h2, kx2, h2 remission plus n0 I. Okay. This is differential entropy of y minus log this of what? What do we have here? User H2 kx2 H2 remission plus n0. Okay. All right, now we can just start applying these rules again. Sum of logs. Then this one. Side. Sum of logs is a product of logs. Log of product, sorry. And then we have product of determinants. Det A times det B is the same as det A times B. Okay. So we can write these. We have inverse here. And these cancel each other. And just multiply. So in the end, some of these terms cancel out. So when we multiply this with this inverse, this is identity matrix, right? So we have log det of identity plus we can multiply from the left. So we have h2 kx2 h2 plus n0 I inverse h1 kx1 h1 remission. Right. Good. So this is the rate of user 1 at point A. Right, because user 1 is equaling first. So there's interference from user 1, which needs to be widened. Right? You can actually call this as, let's say, R1. So this is actually equivalent to log 2 I plus R1 square root inverse times H1 kx1 H1 remission R1 inverse. Right? We are using det I plus AB equals det I plus BA. Right? We're splitting. So here we are splitting R1 to R1 square root times R1 square root, right? And then just taking the other square root to the other side for R1 inverse. R1 inverse. So basically you can then call this as a widened channel. Equivalent channel user 1 after widening it. Makes sense? User 1 is user 2 is there as an interference. So you have to use some pre-processing. If channels 1 and 2 happen to be highly collinear, this will be a huge loss, right? And you try to widen it, right? But they happen to be fully collinear, then this goes to 0, right? And similarly for the other decoding order, you get the same expression, just change the indexes. Okay, so this was for the one fixed channel covariance matrix. But recall from the beginning that we can choose any pair of kx as soon as they are feasible. Right? There's full flexibility to choose kx. Kx does that. It's a matrix of complex values. Have full flexibility of choosing those. An infinite number of options, right? To choose this kx, right? So two arbitrary pairs of transmit covariance matrices you can plot separately, like two pentagons, right? This pentagon corresponds to for example, you can choose kx to be diagonal, right? And equal power loading across hundreds. Right? This is unfeasible transmit strategy. It could be this one here, or then you can choose kx one, assuming no interference from user two, that's the SVD, and similarly for a user two, no interference from user one, assuming just choose kx from the SVD, and this could be another transmit covariance matrix. These are two valid strategies, right? They are feasible strategies. Now, if you have these two sets of covariance matrices in your toolbox, you can clearly see that the first strategy favors user two, right? If you want to, if you have just these two sets of covariance matrices that you can choose from, like in the toolbox, then if you want to favor a user one, this is the first step of covariance matrices, right? In fact, this happens to be also better predicted from the user one perspective. But if you want to give absolute priority for user one, right, this point, for example, then you should choose the second set of covariance matrices. Now, so we have here basically 1, 2, 3 outermost corner points that are interesting. This point here is not so interesting, right? Not a good strategy. You should always use this transmit covariance matrix. Using this transmit covariance matrix and decoding user two length is not a good strategy, because this would be the grade of user two. If you want to decode user two fast, you should always use this transmit covariance strategy. If you want to decode user one last without interference from user two, you should always use this strategy, right? Using this strategy is clearly worse from user one perspective than this strategy, right? Everybody can see this. So this would be a simple selection between two strategies, which user you want to privatize. And then we can add, of course, all these points between A1 and A2. And time sharing between these two strategies. If we have a 50-50 share between these two strategies and choose to decode user one first, user one length, we should get this average. Great. Okay. So maybe we have a look at this graph. Just an example for two, say, random selection of transmit covariance strategies. Now, if you have a possibility to go to all possible, well, infinite number of possible transmit covariance matrix realizations, where each realization corresponds to one pentagon, you can simply plot them on top of each other and connect the points. This would be the convex hull. Right. And then the union of convex hull is just connect all these outermost points. And then you get the full feasible rate region. Right. Of course, this exhaustive search is not feasible strategy. So what we do in practice to find these points, these outermost points, is weighted sum rate maximizers. What it means that we set a weight difference, a relative weight ratio between users 1 and 2, and try to push the rate as high, the sum rate, weighted sum rate as high as possible. So if we have the rates are equal, basically we want to find a point of pair of points, it happens to be a pair of points or this modular case, where this weighted sum is maximized. Basically, we are just pushing our sum rate to a certain direction, right? Find a point where its tangent is defined by this law. Tangent, Argus tangent of -1 is -45 degrees. Right? So this is 45, -45. We try to push this sum rate as far as possible, such that the tangent crushes the rate region. This is a way to understand. Now, if you want to find another pair, let's say, where user 1 is 10 times more important than user 1, then you have slope given from -10, and Argus tangent of -10 is approximately -84 degrees. It would be here. You're trying to push this sum rate as high as possible with this tangent. And similarly, if you have slope defined by ratio 1/10, maybe here, this would be -4 or 5 degrees. Right? So now the way to find this rate region is to change. Just make a grid, sufficiently fine grid of different ratios, starting from close to 0, close to 1, and solve the weighted sum rate maximization problem. We know these points already just by solving single user capacity, SVD. Right? These points are easy. This would be log bit I plus H1, KX1, H1 permission, where KH1 is P1, P1, P1 permission, right? And similar for this. These 2 points are given already. You don't have to solve the weighted sum rate maximizers. So then you just need to find all these other points with a certain sufficient grid. They're starting from 0.01, for example, to 0.99, right? And 100 points, for example. You get a pretty good granularity. You solve 100 problems. So how to solve this? This is in general. Okay, users, weighted sum rate, weighted sum rate over all users, subject to where the optimal variables are random covariance matrices, subject to individual power constraint. Right? The trace of the covariance has to meet the power constraint. And then those rates have to belong, this is the most important, rates have to belong to the feasible region. Feasible region is in like this. Okay, this is a complicated problem in general. Also why from 2 user case. There's the next lecture starting at 12. Let's see how far we get. What did I want to do?
To show why this is complex.
Okay. All right, so we have 2 user case. We want to maximize given maximize weighted sum rate. Let's say mu1 R1 plus mu2 R2 such that kx k they are positive semi-definite and the trace of kx k small or equal to k. Okay. So let's assume now that let's say user 1 is decoded last. Okay. Let me see. So weighted sum rate expression. And user 1 is decoded last. So no interference, right? So mu1 times log det I plus h1 kx1 h1 permission, right? This would be the rate in general. Now the covariance matrix can be still anything, but if the because user 1 is decoded last, it means that user 2 has to be decoded first. No interference, so this would be the single user capacity for user 1. But then rate of user 2, we already computed previously. What would be the rate, like for this particular case? What would be the rate of user 1 if decoded last, or user 1 is decoded first? So there would be interference from the last decoded user. Okay, so in this particular case, the rate of user 2, since it's decoded first, would be log det I plus. Then the interference would be H interference from user 1, H1 kx1. H1 permission plus N0 I inverse times H2 kx2 permission. Right. This would be now the objective function. Right. Where it is a maximize this if you just plug in these values. Right. What can we say about this this function, is it convex, concave with respect to the transfer covariance matrix? Okay, it's one.
That is fine.
It's
Convex.
concave.
Concave.
The function is a concave function with respect to the transfer covariance. What about this one? Is it what about kx2? Well, it's concave function with respect to kx2. Okay. What about kx1?
Oh,
Convex function with respect to kx1.
yes.
So this problem is not jointly convex nor concave with respect to kx1 and kx2, right? This part here is concave with respect to kx1, but convex with respect to kx1 over here, while concave with respect to kx2 here. Okay. So it cannot be solved.
So for even for kx1 is not convex, it's nor convex
Yeah,
nor concave.
it's a sum of concave plus convex.
So this log, the second log is not convex based on kx1.
It's
It's
convex.
nor convex. If
No, this is convex with respect to kx1. This is concave with respect to kx1, but it's not jointly.
I
guess if we take it out,
contract and do the things.
it is nor convex, not concave. If we take this out of log, I guess it should be. I'm not sure.
Well, it's a difference of convex.
Yes, difference of convex.
It is difference of convex.
That second term is difference of convex.
Well, you can write it as a difference of
Oh,
convex.
yes.
You can take them minus out, right? But after some steps. And then of course you can approximate and blah blah blah. Okay, but that would be suboptimal. Okay, so the main thing here is that it is not jointly convex, not jointly concave with respect to kx1. Okay, so it cannot be solved in this form. And of course, if you assume the other decoding order, you just change the indices, same problem. Okay, but you can make a very nice trick to reformulate the weighted sum rate maximization. Again, the rate depends on the decoding order, but so that we have this pentagon for any kx, fixed kx, this is pentagon. Right? So if we have this strategy that mu1, the weight of user 1 is higher than user 2, right? So we are in this region. Weight of user 1 is higher than user 2. The user 1 is decoded last. Okay? User 1 is decoded last. So it gets the single user capacity. User 2 gets the remaining capacity. Instead of writing user 2 capacity directly from the log text, I will add the C sum, is the sum capacity R1 plus R2 minus 1. Right? Of course, you get the same result as if you just plug in there. You get the same result from not convex, not concave. But now we have this, we can express R2 as C sum minus C1. And we know that C sum expression, this one, and C1 expression is this, right? So let's see. All right. So now we plug in R2 right here, and C1. Here's what we have. Weighted sum rate maximization is equivalent to mu1 plus mu2 C sum minus C1. Between the rate remaining for user 2 after removing the single user capacity of user 1 from the sample. Okay, then you just rearrange and you get this independency result that we have a summation of two concave formulas. This is concave as long as mu1 is larger than mu2. If mu2 is larger than mu1, this would be negative. The negative concave would be convex, right? So it would not apply to the case where mu2 is larger than mu1. But then, if mu2 is larger than mu1, then this means that user 2 is decoded last. So R2 is C2, and R1 is C sum minus C2, and again mu1 R1 plus mu2 R2. In this case would be mu1 times C sum minus C2 plus 2 C2, which is equivalent to mu2 minus mu1 2 plus mu1 times C sum. Okay, again a concave. If mu2 is larger than mu1, this is positive times concave function, and this is concave function here as well. So convex optimization function. So what remains is just to plug in these formulas into the weighted sum rate expression. Okay. So we have in this particular case the weighted sum rate 2 times C sum. This is some expression here. Okay. mu1 minus mu2 times the single user expression of user 1. Okay. And here we have a concave objective, right? This is concave with respect to both kx1 and kx2. This is concave with respect to kx1. And this you can plug into CDX and so on. These are the constraints. You have individual power constraint and then positive semi-definite constraints. This is a concave or convex optimization problem, concave objective and convex constraints. Maximizing concave function is the same as minimizing minus concave, right? It is convex. This, for sure, there will be homework where you are asked to solve these problems. Okay, as we discussed already that in all these points, just by deriving this mu, you just make a function which is the function of mu1 and mu2 or whatever vector of mu's, and then that's solve it. Just change this values. Okay, and it can be any. They don't need to be. What matters is the ratio. The absolute values of mu's can be any, right? Because they cancel out in the objective. You can have 1 million over 100,000, the same as 10 over 1 over 0.5, right? No difference. Okay, we have these different points here. This is quite an interesting point. How would you optimize the transmit covariance matrices for point A? You don't have to solve. My hint is that you don't have to solve weighted sum rate function of this. How would you solve the transmit covariance matrices for point A? User 1 is interference free. Right. So how would be the covariance matrix for user 1? What is kx1? Point A. Single user. What is single user optimal covariance matrix. User one.
Single antenna.
SPD.
Okay.
What should be KS1? As if user 2 is not there. Point to point minimum.
Again, minus. Okay. You
Yes, what is the transmit? If the user 2 is not there, not at all, right? Point to point minimum. What was transmit? What is the capacity optimal strategy?
Point to point minimum.
Point to point minimum, right? SPD, right? What is the covariance matrix? Single vectors, photo healing. What is the X? H1 is assuming H1 I mentioned this already. Really too simple. Let me refresh your memory. Here, PPV 1, P1, P1, permission, right? The channels are filling on optimal KS. So this is the point to point minimum, right? The KX that maximizes the capacity in a single user case is equivalent to V permission, where V is the right single vector and P comes from the global field. Okay. Okay, so KX1 is simply V1, V1 permission. This would be the transmit covariance matrix. User 1. It's decoded last without any interference. So also the transmit strategy can be designed assuming no interference, and that's the point to point minimum. This would be the maximum rate. What about KX2? Okay, this is a bit more complicated. Since the rate is right. So user 2, as in user 1 is decoded last. This is the point here. We already computed this. It's log that I plus interference H1 KX 1 H1 permission plus N0 I minus the inverse H2 KX 2 H2 permission. And this is the rate expression of user 2. Now again we can make this, we can declare this to be R2 inverse, same as R2 square root inverse times R2 square root inverse. Right. And then we just use the that I plus AB equals ZI plus BA rule I plus R2 square root inverse H2 KH2 H2 remission R2 square root inverse. Okay, R2 is this one. So you could write this directly as H1 KH1 square root inverse both sides, but it gets messy. Okay. Now we can, since we have already fixed the transmit strategy of user 1, KX is given. So this we can compute. Okay. This is a known matrix. R2 is a known matrix. We can compute it, right? We can take an inverse of it. We can take square root of the inverse. So we have, this one is another matrix, right? So fixed numbers, okay? So we can declare it to be H2 tilde, okay? And H2 tilde. So it's equivalent to point-to-point MIMO with whitened channel, okay? And then KX is simply, what you do is H tilde 2 equivalent to the U tilde 2 lambda tilde 2 times B tilde 2 permission. So you know that KX2 has to be then B tilde 2 times P tilde 2 tilde 2 permission, where P2 comes from the water table over this diagonal values. And that's the solution of transmit coordinate matrices. Okay, makes sense. And similarly for point D, it would be here. Just change the indices. Okay. When you compute this rate region in your homework, you can get these points already directly from this formula. Okay, and then you can proceed with the rest. Okay. Some rate optimal solution is also simple. You know, when the weights are equal, it gets simple. Okay, it seems there's a new lecture starting, so let's continue. Okay, thank you. Joo, nyt on valmis.